Hi, my name is Aarti Singh and I'm a graduate student at University of Florida in the Department of Electrical Engineering. I'm gonna present my report demo for the final project for the class of EEL 6935 Network Science and Application for the fall year 2014. My topic is called Analysis of Minimum Spanning Tree Based Clustering Topology Control, and which is done in wireless sensor network. And my supervisor has been Dr. Tapangu. I'm going to be outline first. We're going to start with the definition of WSN and the uses it has in the industry and in the society, and the issues it faces, and, and the general solution that we can obtain with the help of clustering, which is clustering. We're going to study the clustering techniques. Um, the main topic is the MST based uh, clustering topology control, which is the minimum spanning tree based control, and I have done MATLAB programs for it. So I'm going to show you the results, and we're going to conclude with the results that which one I found to be better. So I'm going to start with the wireless sensor network definition. What basically it is that it's an autonomous group of sensor nodes which can be numerous in numbers, and they're deployed remotely, and they're controlled remotely in flight, and their objective is to pass information from one point to another. They are rarely used in environmental monitoring and military services. One trait that they have is that they collaborate with each other as well as they communicate with the base station, and they can be on a constant move. So the problem that we face in these kind of networks is that they are always facing energy deficiency, and their efficiency for the efficiency of operation is really low. What happens is that they are always switched on, so even if they are not communicating with anyone, they're constantly losing power, and they're having a limited source of battery power. So it's a bad news for anyone who's highly depending on certain sensor node, because it might just die and it will affect the entire network. We're gonna have some prospects, some ways so that we can reduce the loss that's there, and we can reduce the dependency on nodes, because we can hop around and have some algorithms that can help us and not depend on just one node. So as I said, that power is consumed, and it's lost also, and because since node can just die and just get lost, uh, can lose all its power, so they want to be a connectivity issue. Autonomy is really a big issue with wireless sensors. They should be autonomous enough to know when to shut down and to not. If they are not having anything to transfer, they should be aware of the fact that they're not supposed to transfer, they're not supposed to be on. And other than that, we have the issue of scalability, because these are really big in numbers, they're really high in numbers. They should be able to collaborate with each other very efficiently. So yeah, these are the issues that they're facing. And as I said, they can be on constant move, so they are operating in an ad hoc network in which they can make topologies and make break topologies as they please. So, so they have to be, as they are on constant move, they are supposed to have different. They can have different powers, they can have different densities, they can have different locations. So all of it depends. All of it actually makes them vulnerable to have less efficiency and have more power loss, because it might be that something is really far and it can't transmit, but it's actually taking all its energy to be on. So that way it's actually bad for the system itself. So how does graph theory work here? So as you can see, we have a high number of spread out networks. We're gonna represent them as a graph. So what a graph is just a collection of nodes and the way they are connected. It's called links, and usually they are represented with the weights. and the weights can be represented with, let's say, the size of the length which they are connected with. Someone is far, someone is close. So that's how you can, that's how you say that a node, I'm sorry, a network of sensors can be represented with a graph. Why do we do so? Is because that there are tools like in MATLAB or a simulator where you can manipulate this graph and make something sensible out of it, and manipulate it in such a way that we can learn the traits of that graph, and so that we can, put them to better use, so that we can have better topology of the network. So that way graph theory works. One good thing about graph theory is called clustering. Basically, if you have a big graph, you can chop it down to smaller graphs, and it's always easy to control smaller graphs. We can apply many algorithms on the smaller subgraphs and come out with a simplified version of the subgraph, and as we're gonna see later. So that's always easier to have subgraphs. Well, the ultimate goal is that we want to have a network which is cost effective, that is, which is not losing energy and power. And splitting, that is, graph partishing, actually helps it there. How we do graph partishing is k-means. One of the methods is k-means. Other is mean distance method, and then there is called hierarchical method, hierarchical clustering. So all of them are going to be discussed here. So what happens is when you have produced a graph, when you have produced a subgraph, which I'm going to call cluster from now onwards, it will have cluster members, and then we're going to choose cluster heads. What is the role of cluster head? Basically, for example, the cluster members are not going to communicate with the base station. They're going to have all the information sent to the cluster head, and it's going to communicate with the base station. So in that way, we can have someone to represent all the information within the cluster, and it just gives you less nodes to worry about. But there is one catch, that we have to have clusters made such that cluster heads are just one hop away from the cluster members, that CNs, so that they just have simplified topology. Whereas cluster heads can connect to the base station in a multiple hop pattern. That means it's not necessary that the cluster head that is very close to the base station will be getting connected to the base station through that path. It might be that the path has higher weight, so it will actually it won't connect directly. It will actually, it can go from any other direction as well. So one of the way to do clustering is called k-means, which is basically just a distance dependent clustering. How it works is that you get to choose the mean for each and every point within a cluster, and then you just take the within cluster sum of squares, which is x minus mu I. Mu I is the mean, and say we have k clusters. S represents a cluster, and x is the point of node that were the original points. So what we are doing is basically we are getting k clusters from the original nodes. So how we implement this thing? Well, MATLAB has a straightforward command called k-mean, which is put k-means into the control panel, and we get the clusters. Another method is called leech, which is low energy adaptive clustering hierarchy. It's basically a hierarchical clustering algorithm. What happens is that you make cluster heads such that they are just momentarily, first of all, and then they are autonomous. And then you repeat the iteration so that each and every sensor node becomes cluster head once. And cluster members are just connected so that they are closest to the cluster head. I'm going to show you this leech program so that you get an idea on how it's actually operating in MATLAB. It's really interesting to see. And there are certain properties of cluster heads. First is that they should be distributed uniformly, and it's the cluster only that will actually exchange information base station, not the cluster members. And as soon as we are getting the clusters, we are gonna have We're going to have the information delivered from the cluster members to cluster heads such that they are cost effective, and such topology we can apply only with MSTs. MSTs are, they stand for minimum spanning tree. So it's topology control of all the nodes is really important because it is actually going to give us lower number of um, power loss and higher efficiency. MST itself is an algorithm, as people in computer science will know. It actually gives you a tree which spans through all the network. That means it touches all the nodes, but the total cost to connect all the nodes is the minimum. That's what MST is. So here comes the main point of our topic. It's called MCTC, which is MST-based clustering topology control algorithm. It is performed on the cluster, and once you have obtained the cluster head, it is performing all the cluster heads so as to they can communicate with the base station. So as you can see, there are going to be two tier structures. One is cluster members, and the other one is cluster heads. So how it's done? So we start with this algorithm. It's a pseudocode basically here, but this is how it's done. We assign weights. Weights are certain attributes. It can be energy, it can be distance. So what you do is you say that whichever cluster is really close, the probability of it having probability of it being a cluster head increases. So that's how weights are assigned. And if you are having an ith node which has the highest weight, it will become the cluster head. Otherwise, someone else become the cluster head, and all the other will become cluster members. One thing to note here is that weight here I have taken only distance space, not on energy or not on IDs. As I said before, cluster heads have to be selected, and they should be just one hop away from the cluster members. So why do we actually need topology control? Topology control is needed so that we pass information with the minimum cost, as I said earlier. So this minimum spanning tree is done with Prim's algorithm. It's an algorithm I have applied in the code that I'm going to show you. And once the clusters are formed, you're going to run MST inside the cluster as well as on the cluster heads that are going to come from the cluster. And one thing that's really important to know that, as I said before also, that between cluster head and base station you can have multiple hops, while between cluster heads and cluster node you can have just one hop. Okay, so it's time for the MATLAB code and results. Here is my main MATLAB code. What it's doing is that I have taken for one instance n equals 1000 as the total number of nodes. They are distributed randomly, and usually we take from 5% to 10% as cluster heads. So I'm going to take the number of cluster as 5%. So yeah, here I'm taking k-means, and I'm gonna have the values coming out from k-means to be put in IDX, CTRs, cluster sum, and D. IDX is gonna be telling you that how those 10,000 values were placed in which K. K will give you 50 clusters. So how those 50 clusters will be having the values, and which one will be having which values. So similarly, CTRS will give you list of centroids of each cluster, and CTL sum will give you within one cluster what is the link length. For example, one cluster will have many cluster members. All of the distances will constitute the link length of one cluster. So it's going to give me 50 rows and one column. And similarly, I get D, which will be how the 50 how the entire 1000 points in fact are distributed for the 50 clusters from the first 50 clusters. This is just for the degree means, this is just for the calculation purposes. Here I'm actually getting my cluster heads with the help of centroid that I uh, got from D, and with this thing I am going to plot it. This is just for again for the calculation purposes. No, I'm sorry. This is for the k-means. I'm going to plot a k-means graph, and then in that k-means I'm going to get clusters. Clusters will have the intra-cluster thing, and then the cluster heads that I'm going to get will give me another MST, minimum spanning tree. So that is it. Let me just see how can we run this thing. These are just the printing value commands, and I'm gonna run it now. So yeah, you can see these are the graphs that I got. First one is without any topology, just the k-means graph. You can see there are 50 clusters, and they are spread out with on a normalized thousand nodes. These are 1,000 nodes, and I've normalized the axis. This is without any topology. Now you see that this is for MST. This is without any topology control, but there is MST for the entire graph. And then you can see this is the MCTC based clustering, and you can see the minimum spanning tree. Everything is connected. One thing I can show you here is the reach, which I have to make different separately. If you see, this is for 100 bits, 100 points. As I was saying, that cluster heads are actually shifting, and this is gonna keep happening until all of them are covered as cluster heads, and they're gonna have their original, they're gonna have their individual clusters. So this was it. Let me just, it's not gonna stop. So I'm gonna show you how what I have got from the results. These are the compared results. I can see that MCST is standing out in all of them. It has the minimum average degree as well as minimum average link length. So it actually performs better from just MST, Reach as well, and without any topology. There are other control topologies out there, such as neighbor control topology, clustering topology control, which give almost equal results, but MCST is better for large number of a very big number of nodes. So this was it. I am gonna attach my report, my video, and my PPT on the e-learning site. Thank you for I wanna thank Professor Wu for his time and for guiding us throughout the class. And this is me signing off. Bye.